Hey, what's up? I'm Joachim, and in this tutorial we're going to create a stylized popping corn animation. In true New Year's Eve fashion, we'll start by creating a particle simulation that will drive the overall motion. We'll then use this particle sim to instance some geometry, and after this we'll create some procedural corn textures in Houdini's GPU-based compositor Copernicus. We'll then be able to bring those textures into Redshift in order to create the final look, and I'll also do a quick walkthrough of Redshift's new displacement feature and show how we can leverage displacement to add detail and depth to our geometry. This will be more of an entry-level tutorial, but it's a great opportunity to explore how different parts of Houdini can work together to create something simple and fun, yet visually dynamic. So with that out of the way, let's dive into the tutorial.
Here in Houdini, I've gone ahead and created a geometry container, and inside of it, I've just made a simple sphere. So it's a sphere, and then I'm subdividing it. I'm adding some UVs, some normals, and then I have this null called outCorn sphere. Let's start by setting up the source geometry for our popnet. I'm going to create a circle. And this circle, I'm going to change the orientation to be on our floor. And then I'm going to up the subdivisions to 50. And then we can add a scatter swap. I'm going to change the force total count to 25 so that we have 25 points. And then I'm going to up the relaxed iterations as well. We can then drop down a enumerate swap. And this will create a ID for all our points. But we need to change the group type from primitives to points. So now in our geometry spreadsheet, we can see that we get an index here. I'm also going to create some point velocities. And I'm going to check the conical noise. And then if I click this button here, we can display our velocities. Right now, they're pretty small, so I'm going to up the scale to 60. And I'm going to lower the cone angle to 15. I'm also going to change the global seed, something like 99. So now, when we spawn the particles, they'll essentially shoot up in the sky, which is exactly what we want. So with an attribute adjust float node, we can then create a new attribute that will define our emission frame. So I'll drop down a attribute adjust float. And in the attribute name, we're going to call this emit_frame. And then I'll want to change the pattern type to remap attribute. And the min value will define our starting frame. So in my case, that's going to be 1001. And then we want to stop emitting at frame, let's say, 1096. We can then remap this attribute by another attribute. We'll then take that index attribute we created earlier and set the source range to be between 0 and the total number of points on our geometry stream. And we can grab this by typing in an hscript function called endpoints. And this needs the first geometry stream, which is 0. And then we can subtract 1 from that, so this returns the maximum amount of points. So now if we take a look into our geometry spreadsheet, we can see that we get different frame values for each point. However, right now they're decimals, so what we can do is we can click the step size, and then we can up this to, say, 2. So essentially what this will do is create whole frame numbers. So the emit frame attribute will dictate when the particle should spawn into the pop sim. So from this, we'll want to create a group that toggles on and off whenever the current frame number matches the emit_frame attribute. So we can create a group with the group expression node. And I'm going to change the group type to points. And then I'll just name this group emit. And then in the expression field, we can say at emit_frame is at frame. So whenever the timeline matches the emit frame attribute, the group will return 1. I'll also want to create some random rotations, so I can add down a attribute randomize. And in here, we can set the attribute name to be orient. And this needs to be a 4-dimensional vector. And I'm going to change the distribution type from uniform to inside sphere. So now when we've prepped our source geometry, we can append the popnet. Inside the popnet, we have all the basic components needed to create particles. If you're new to Houdini, the main important thing to understand is that this context works a bit differently than how things work in SOPs. In SOPs, operations normally flow like top to bottom, but in DOPs, operations flow left to right, top to bottom. And this order of operations is pretty important to understand since simulations are based on the result from the previous frame. In the pop source node, I'm going to change the emission type from scatter onto surfaces to all points, since we have points that we want to emit from. And then I'm also going to change the source group to that emit group that we created in subs. So if we zoom out a bit, and I'm going to turn off the display point trails. So now if we hit play, we can see that we get points spawning based on the group. Next, I'm going to go into the birth tab, and I'm going to set the life expectancy to 0.6. So after they reach a life greater than 0.6, the particles will die. So the idea here is that we'll want to spawn new particles whenever these initial particles die. And the popnet actually creates an attribute for this. So if you go into pop object geometry and search for dead, we can see that it creates this dead attribute, and this will toggle to 1 whenever a particle dies. And we can use this to set a stream. So if I do pop stream, we can create a new stream. And in the expression editor, we can say ingroup equals to I at dead. So now whenever a particle dies, it will enter this stream. So in order to visually keep track of the particles, I'm just going to add a pop color. On our primary particles, I'm going to make them red. And then on the second stream, I'm going to make them green. Right now, we won't see any green particles because we haven't spawned any particles. I'm going to change the constant activation to 0, and then I'll up the impulse count to 25. So now it'll spawn 25 new particles for each particle that enters the stream. So if we take a look at the simulation, we can see that we are indeed spawning new particles. Something that also can be useful is to enable this JustBorn group, and this will add any newly emitted particles to this JustBorn group, but only on the initial frame when it gets spawned. And we'll use this group in a second. I'm going to go into the shape folder, and I'm going to change the shape from sphere to point. So now the particles will emit on that same point coordinate as our initial particles. And I'll also want to modify the velocity. So by default, it'll just inherit the same velocity as our initial points. So I'm going to lower this to 0.1. And then I'm also going to add some random velocity. So now they burst outwards. I'd like these secondary particles to have a bit more oomph or like pop to them as they get emitted. So what we can do is we can add or we can scale the velocity on the first frame where they get emitted into the system. So I'm going to pause, and then I'm going to make some room here. I'm going to append a pop wrangle. And in this pop wrangle, we can operate on any particles that are inside of this JustBorn group. So what I then can do is I can say v at v for velocity, and we can scale this by, let's say, 20. So now they get a lot more velocity, but only whenever a particle is in the JustBorn group. If we don't use the JustBorn group, essentially what would happen is that the velocity would just get multiplied on every frame, and they would go crazy. I'll also want to create some gravity, so I can add a pop force node here. And I usually just grab the gravity setting from the gravity force. So I'm just going to copy this over, paste it in here, then I can delete the gravity node. So now we have some gravity. And I'm also going to add some drag to this. So I can do a pop drag node. Let's try 0.5. So with the drag, we get initial velocity that's pretty fast, and then it will sort of taper off the longer the particle has been in the simulation. So we get this popping effect. So now when we have our basic particle simulation, I'm going to head up one level. And then I'm going to add a copy to point stop, wire in our sphere. And then we can use the popnet as our source for instancing. I'm going to click pack an instance. And if I hit play, we can see that our spheres are getting instanced on our particle sim. But right now they have the same scale. So let's modify the p-scale. I'm going to click this button here to lock the viewport. And then we can head back down into our popnet. And I'm gonna create a pop properties node right after we replicate the particles. And in here, I'm just gonna say uniform scale to 0.33. So now these particles get smaller, but I'd like to remap them so that they scale down over time. So what I can do is I can enable this use of expression field. And if we hover over the uniform scale, we can see that this parameter is called pscale. So we can modify this by typing in pscale. And then I'd like to remap this parameter. I'm going to use a channel ramp for that. Call it remap pscale. And I'll remap by an internal attribute called f@nh, which stands for normalized age. And what this is a value between 0 and 1 over the course of a particle's life, which is great because the ramp expects values to be between 0 and 1 in order to fully remap them properly. So I'm going to click this button here to create the ramp. And if I hit play now, you see that now they're gone. And then they slowly scale over time. But we actually want the reverse. So I can just do this. And then I'm going to remap this. I'm going to set it to B-spline. Maybe do something like that. So now they'll scale down over time. I'm also going to change the life expectancy here to maybe 1. And then the life variance can be like 0.1. And right now I'm actually overriding it. But I actually want to multiply it so that we keep this initial value. So now if I hit play, they start at their initial value and then they scale down over time. However, I'd also like to add a little bit of a sort of character to the simulation. So what I think we can do is add a little bit of anticipation to the initial particles. So right before they pop or die, they should scale up a bit. So I'm going to copy this pop properties node. I'm going to change the uniform scale back to 1. And then I'm going to remap here. So I'm going to set the value to 1. I'm going to create another point here. And then right before it dies, let's boost the scale by 1.5. So if we hit play now, they have this slight scale to them before they die. And I find that small modifications like this can really add a bit of character and flavor to a simulation. All right, so next up, I'm gonna head up one level and let's model a kernel. So I'm gonna move this out of the way a little bit and then I'm gonna create a box. And this box, I'm gonna scale down in the Y to 0.61. I'm gonna add some more divisions. And then I'd like to taper this a bit so we can do a linear taper. I'm gonna set the capture origin to 0.5 and then the capture direction to -1. And then we can taper this off, like so. I also want to have UVs, so I'm going to add a UV unwrap. And then set the spacing to 0. And I'd also like to bulge this shape a little bit. So we can drop down a bulge node. And this bulge node needs a magnet or a metal ball. And then we can up the magnitude just a little bit. So this metal ball is going to act as sort of like a fall off for this bulge node. I'm then going to add a match size node. Check scale to fit to roughly match it to a unit of 1. And let's also add some bevels. Maybe set the distance to 0.1. And I don't want to bevel all of the geometry, so I can hit this ignore flat edges, up this to 25, and then I'm going to up the rounding to 2 as well. Lastly, I'm just going to subdivide this, and then we can create a null call out_kernel. So this is our kernel shape, and obviously you can modify this as you wish. This is just like a simple representation. Then let's instance this on our secondary particles. So after the sim, I'm just going to split this geometry into 2 different streams. We can pick the stream source first input. So on the left side, we're going to have our initial particles. And on the right side, we're going to have our secondary particles. So I can copy the points up. And then instead of the spheres, we're going to instance the kernels. So if we merge these streams, we're now instancing the kernels. However, they have sort of like the same orientation, and that's kind of boring. So let's add some spin. All right, so I'm gonna hop into our popnet, and here I'm just gonna do some housekeeping. This is scale velocity. So let's add some spin. So we can drop down a pop spin, and by default it'll just spin on the y-axis. And this usually needs to have a pretty high value. So you can see now that it's just spinning in one dimension. But what I'll do is I'll set the axis based on the velocity direction instead. So first I'm going to create a vector, call it there. And this vector will be the normalized version of our velocity. So to visualize this, I'm going to unclick this button here. And then if I click the trail, so essentially what we're storing is this vector here, but we're normalizing it to have a length of 1. So I can overwrite the axis by the direction vector that we created from the velocity. So now each particle will spin around their velocity direction. In my final animation, I think I actually crossed this with a constant. If you want to learn more about how cross products work, I'll leave a really good tutorial made by Peter Claes in the description of this video. But essentially what a cross product does is it returns a vector perpendicular to, in this case, the direction vector. I can then take this pop spin, just duplicate it, and instead of 5,000, I'm just going to lower this to be a value of 300 because I just want these to spin a little bit slower. And then I can also add a pop drag spin. I think I set this to 2. And if we play, now they get an initial spin and then they sort of like slow down. And that's it for the simulation part. I'm just going to cache this out. So first I'll want to clean these of any attributes that I don't need. Let's keep ID, let's keep velocity, let's keep orient, and let's keep p-scale. I'm going to uncheck these. Then we can file cache it. Call it particles. Save the disk. Boom. And then we can create 2 nulls. Call the first one out render corn. And then the other one we can call out render kernels. So then if I head back up 1 level, I'm going to create 2 geometry containers. I like to color these green. And then in here, I'm just going to add a object merge. And then we can navigate to our render corn, copy this, paste it in here, pick the render kernel. So now we have both the geometry streams, and I just need to uncheck this viewport lock. All right, so let's set up the textures. I'm going to build these textures in Copernicus. So I'm going to drop down a copnet. And inside of the copnet, we can create a whirly noise. So what we're aiming to do here is to create some sort of like displacement texture that resembles some corn. So what I found worked is if I reduce the jitter size a little bit, and then in the post-processing, we can hit this complement button, and this essentially inverts it or gives the absolute values of the noise. And then I can lower the bias a little bit, just get a little bit more contrast. And we can also add contrast in here, something like that. And then we can remap this. So I think I did something like this. I was just trying to get sort of like a flat area at the top, and then they should sort of like round off into these darker areas. From here, we can create a null. I'll call it out_disp for displacement. So we have our displacement texture, and I also want to create a diffuse texture. So I can take the output from our remap node and create a ramp RGB node, and we need to pipe this into the position. So now we're remapping or adding colors to this grayscale image. Essentially what I did is I created this yellow corny texture, and then just by looking at some reference images, I noticed that corn sometimes have these like wider kernels. So I created another ramp that was a little bit brighter. So with these 2 ramps, we can mix them, and we can do this if we put down a over node, and then we can pipe these inputs together, and then we'll create a mask. And we can get a mask by converting the ID output from ID to RGB. And this will give us color values for each sort of like cell from the noise. And then we can convert this into a grayscale by using the RGB to mono node. So we get something like that. And then in order to add a little bit of detail back in, I think I multiply this by the remap as well, so that we get some shadows in there. I then took this multiply node and remapped it and piped this remap into the mask. So now I can sort of dictate how much of these white spots that I want to have in my diffuse texture. And then I added a null, call it out diffuse, and those were my textures. So I'm just going to copy paste the exact values I had in my intro animation. But yeah, it's the same stuff. So when I was testing this, I also dropped down like a preview material node. And this is pretty cool. You can preview your textures. So I fed in the height, just did some remapping here. And by default, you'll just get a grid, but you can change between these presets. By the way I'm pulling in these reference images is with a free software called PureRef. So if you go to pureref.com, and what this does is it creates this infinite canvas where you can drag in your reference images. It supports alpha, super useful tool, and I use it all the time. All right, so finally, let me just show you how I set up the Redshift shaders. So I'm gonna cheat here and just drag in some basic lights that I had. It's nothing special really. 3 lights, 1 light at the top, 1 key light, and 1 fill light. And the fill light has a little bit of warmth to it. So if I hop into my camera, pull up a frame, go to Redshift, and if I hit render, we should get some unshaded spheres and kernels. So the first thing I'm going to do is I'm going to select these 2 render geometry nodes. I'm going to go to Redshift and I'm going to add some object parameters. And since we're instancing, I'll want to go to the instancing tab and I'm going to change this from Redshift proxy objects to Houdini compatible objects. And then I need to check this instance top level packed primitives. So now it will render these as instances. For the tessellation and displacement, we have this new sort of displacement introduced in Redshift. What is it? Like Redshift 2026.2 or something? Anyway, it's like one of the latest builds at the time of recording this video. And by default, it will just grab whatever settings we have in our Redshift ROP. But I think I changed this to be on, and then I changed it from vertex displacement to texture displacement. And I also changed the bake resolution to 4096 by 4096. Which I also need to do on the resolution of the CopNet. So I'm going to change this to 4K. And then I lower the scale to 0.1. And I also enable tessellation so that we get subdivision on render time. So now when I have this, I can create a new matnet. And I also like to build my shaders in a separate matnet instead of building it here at the root level. I just find it a little bit easier to copy-paste this around into different working files. And if I need to share it with some coworker or some other freelancer. So I usually build my shaders this way, but feel free to build it any way you like. So I can drop down here. I'm going to create 2 RS material builder nodes. The first one I'm going to call Corn. The second one I'm going to copy paste it and call it Kernel. Then I can split this network by either going up here and clicking on the split pane left, right, or alt bracket. And then I'm going to lock this one. I'm going to hit P to bring up my parameter window. And now we can drag our corn texture to the render corn and then the kernel to the render kernels. And in here, we can first set up the corn shader. So I'm going to go in here and then I'm going to get some more room. I'm going to hit render and now we can see that our material has been assigned. So now we want to fetch those textures that we made in Copernicus. So we can do this if we drop down a RS texture node. I'm going to rename this disp for displacement. And then in the file name, we can fetch it by doing this expression here. So first off, we need to write op and then colons. And then within backticks, we can run a function. And the function that we want to run is op full path and then parentheses. And then we add the path within quotation marks. So if we go up 3 levels by doing this, we can find our CopNet. I'm going to hop in there, and here we can grab our out_disp null. So if I hit render and pipe this into the surface, we can see that we're fetching this texture. So this I'm going to add into a RS displacement node, and this will go into the displacement input. And we can already see that we get some displacement. But I want to remap this to not go to 1. It should go from -1 to 0. So that way it respects the boundaries of the original sphere. Next, we can copy-paste this, and I'm going to call this diff for diffuse. And then instead of the displacement, we can add the diffuse texture, like so. And if we take a look at this one, you can see that we are indeed grabbing that diffuse texture. I'm going to pipe this into the base color. And then in the shader, I think I lowered the roughness to 0.1. I upped the IOR to something like, I don't know, 1.615. And I think I actually piped this into the subsurface color as well. So I can pipe this into MS color. And then if I bring the weight up, now we get subsurface. And I also want to color the radius. So I'm just piping in these values here. And this was just from trial and error. So I think I did something like that. It's kind of hard to see here, but. And lastly, what I did was I added some maximum noise as a bump. I think I changed this to displaced turbulence. And I also used the UVs for the mapping. So this looks like something like this. And we can pipe this into a bump map. Lower the height scale to 0.01. It's usually a good starting point. I'm going to turn off the subsurface for now, just to make it render a bit faster. I think we can lower it even more. I think I just did this to break up the specular a little bit, just to get some unevenness of the specular hits. I'm going to drag up the subsurface again. And that's it for this shader. And then for the kernels, I think I copied the bump settings. So I can just copy the bump, paste it in here, plug this into the bump input. And then if I go into the scene file here, I think I added some color to it. I'm just going to copy paste the settings here. So now we have some yellow kernels. I can copy this color to the other stream as well, so that we have a yellow representation of a geometry. And then lastly, I can just fetch this CD attribute by putting down a particle attribute lookup. Usually I like to just name the attribute that I'm bringing in the name. And then here I can set this to $OS. So this will just grab the name. And then we can pipe this to the MS color and drag up the not the transmission. And drag up the subsurface, hit render. And I'm also going to lower the roughness and have the same sort of values here. And that's about it. So in order to get motion blur from instances, you need to go to your render settings, go to motion blur, and let's enable motion blur. And then I'm also going to enable this checkbox here, instances/particle blur. So now if we hit reload, we should get some motion blur. And we do.
And that's it for this time. This will be my last tutorial of the year, but I'm just getting started, so make sure to like and subscribe if you want to see more. Also, feel free to give a shout in the comment section if there are any particular areas you'd like to dive deeper into in future videos. I'm always keen on learning, and the whole purpose of this channel is to create a space where I can share those learnings and experiences with you folks. The working file for this tutorial will be available to download for free on my Gumroad, and the link will be in the description of this video. With that said, thank you so much for watching. I wish you happy holidays, a happy new year, and I'll see you in 2026. Oh, this will have to do.